bit about how we use sound in engineering. I'm going to touch upon a few different topics to give you an overview of how, in a field that you might think that is maybe not very related to sound, we have to consider sound or use sound for certain purposes. So here's an overview of what I will cover today. I'll first talk about a few general applications, and then I'll go into my field, which is bridge engineering. I'll show you what are non-destructive testing techniques based on sound. And one of the techniques that we use is acoustic emission, and that is related to proof loading of bridges. So that's something I'll show as well. And I'll round up with a summary and conclusions. So as for general applications, well, the most obvious branch of engineering that is related to sound is acoustic engineering, and that is defined as anything that is related to design, analysis, and control of sound. So there's a whole variety of applications in here. It goes from noise control, reducing unwanted noise, and I'll talk a little bit about that, how we use noise control in civil engineering, ultrasound applications, as well as the programming the digital sound and synthesizers. Anything that is designing buildings also has to take into account sound, especially if you are looking at, say, a concert hall, where you want a good quality of the sound of the music inside the building. Within a theater, you might want to have very good intelligibility of speech. And for offices, you have to take it into account because you want that nice little murmur in the background, like in a coffee shop where it's pleasant to work, but not too noisy. And this is where architects have to take sound into consideration. Now, when we step out of our buildings, we have our pavements or roads. And all the vehicles that pass over the roads, they cause noise. Can be very noisy, not just the traffic, the honking, but the touch, the friction between the wheels and the pavement. And one solution there, and that's within civil engineering, is to use an open graded asphalt. Same driving experience, more or less same driving experience as regular asphalt, but it's open graded, so it's absorbing some of the sound. So this open graded asphalt is commonly used in the Netherlands, and there it's called Zoap, called whisper asphalt, because it's very quiet when you drive over it. And besides being quiet, it's a very porous mix, so water also drains away. So when it rains, you don't get all that splashing of water. And you see on this picture here the difference between the road in one direction that has this open graded asphalt that is reducing the noise and absorbing the water, and this one here that is a wet pavement. You have splash water, it's unpleasant driving, and you really notice the difference if you cross the border, drive into the Netherlands, and it's raining. Suddenly you don't have all that splash water anymore, and it sounds more quiet in your car as well. So as it said, we have a noise reduction of 4 decibels at 120 kilometers an hour. It might not sound that large of a noise reduction, but it is something. Plus we have the drainage of water, so no aquaplaning, it's safer to drive, and no rutting. Rutting is when heavy trucks pass over a pavement, they leave that trail, right? You feel it, that the tires of the trucks have been there. That's what we call rutting. There's a deformation of the asphalt over time. So it doesn't happen in open graded asphalt. One of the disadvantages, so I said before that our open graded asphalt has virtually the same driving experience as a regular asphalt. One difference is you have a slightly longer braking distance. So typically there are signs saying, especially if it has been newly paved, saying watch out, you need a longer distance to brake. So keep a little more distance between cars. And because it's very open graded, we have raveling problems. Raveling occurs if we have our asphalt, we have the stones and the asphalt binder, the product that comes from oil. If that binder wears out, the stones come out, and those are the little stones that pop out when you drive over that can hit your windshield. So that problem you have. And it needs more maintenance. It has a slightly shorter lifetime. Now, when I go into my own field of bridge engineering, and that's what I'll focus on for today, what we're looking at most of the time now is not in building that many new bridges, but looking at the existing bridge stock and see how we can extend the service life. And there's 3 things that we do there. We are working into getting better calculation methods, working into better inspection methods, and then if the bridge needs to be destroyed or improved, we look at better maintenance and rehabilitation techniques. What I will focus on today is improved inspection methods, and I'll show you how we can use sound to inspect bridges. If we talk about inspection, what is done most of the time is visual inspection. An engineer is sent to the bridge, and he looks at the cracks and looks at the condition and says, I see a little bit of this, and I think it's because of this, and I see a little bit of that. But all you can see is the outside of the bridge. You have no idea what happens inside of the material. And in this case, I'm focusing on concrete. So you have no idea what happens inside of the concrete, how the steel inside of the concrete is behaving. Another technique of inspection is non-destructive inspection. That's what I'll mostly talk about today, is you have a little box, non-destructive testing method, and you put it on the bridge, and it looks what is going inside of the material. Another way is destructive inspection, where you actually go and take a part of the bridge. So you would take a little sample out of the concrete and test it in the lab. But obviously, when you do that, you have a hole in the bridge. So we want to avoid this as much as we can. We might, take a little bit of material out of it and calibrate our results of other techniques with it. But generally, we want to do as much non-destructive testing as we can. And proof loading is another technique. There's 2 types of proof loading. One is where you send heavy trucks over a bridge and see what happens. And the other one is static, where you start to add load more and more, and you follow the deformation, and you listen to the bridge and see what happens. So I'll focus on non-destructive testing and proof loading, because when we do proof loading, we put all these measurement techniques on the bridge as well. So different techniques of non-destructive testing, many of them are using waves, most of them sound waves. So one of them is ultrasound. You mostly know ultrasound from medical applications, but in bridges we use ultrasound as well to evaluate material properties, such as the Young's modulus of the material. That's a measure for the stiffness, but it only gives us an idea what is happening in the surface zone. So it only gives us an idea of the very top of the material. The physical principle behind this is that we look at surface wave dispersion. So it's related to the velocity of propagation as a function of frequency and wavelength. It is applied to a layered system, and it gives us information about the layer thickness and the Young's modulus. It looks something like this. So we have this little card going over the bridge. It has these ultrasound probes, and it gives us as output the Young's modulus, and the modulus varied over the depth of the structure. A very popular technique is radar, not exactly sound waves, but electromagnetic waves, so I thought to include it because it's sort of family. And that can detect objects inside of concrete. Can be reinforcement or wire meshes, another type of reinforcement. And the result is this type of contour maps. So here we have this map, and it says here we probably have delamination, the concrete opening up. Here we might have some corrosion, and the gray part is healthy concrete. Those are more advanced methods. An older method that does work and that is fast is just based on experience of an engineer. He will drag this chain over the concrete, and if it's sounding like a bell, it's good. If it sounds hollow and muted, then there's probably something wrong with the concrete. Or you can use the same principle and tap on concrete with a hammer and listen to the sound of it. Gives you an idea of where you have delaminations in concrete. That is where the material is coming apart. A similar method is echo, impact echo, which is emitting a stress wave in a frequency range of 3 to 40 kilohertz. And then if there is, say, delamination in the concrete, it will bounce back faster than where you have sound concrete. And very similar is impulse response, but that's just in a lower range, 0 to 1 kilohertz. As a conclusion of this part on non-destructive test methods, generally, one method is not enough because you always have some noise on your measurements. So what you should do is combine different techniques. And if, say, your ground penetrating radar is saying there's probably delaminations there, and you're using impact echo, and you're also observing something, then you have more of an indication, yes, there's something going on with the concrete. And on this website, the NDT, or the ND Toolbox, there all the information is brought together for practicing engineers to stimulate people in the field, not just to use visual techniques, but to start adopting these non-destructive testing techniques, because we can learn so much more about our bridges by incorporating just a few of these techniques into our inspections. Another method is acoustic emission, and in this case, we are not applying, in all the other methods, we were either dragging the chain or the hammer over the concrete or applying a wave onto the concrete. In this case, we just put the sensors on the concrete and listen. Well, what are we listening to? Well, to acoustic waves that are emitted by the material. And when does concrete make sound? When something is happening, when cracks are forming or when we have plastic deformations. The waves that are emitted are transient elastic waves in the range somewhere between 1 kilohertz to 100 and typically 100 megahertz. And typically in our bridge applications, we're catching waves between 100 kilohertz and 100 megahertz. And whenever something happens to the concrete, say in this example here, we have a crack that is forming. So the concrete starts to make sound. So these waves go and the sensors catch this signal, and that's what we call a hit, a measurement. Acoustic emission is a popular technique when we're doing proof loading of bridges. It gives us information about cracking that is occurring in the concrete before we can even see it. If the acoustic emission can hear it, it's not the moment that we can see it with our bare eyes. We're talking about micro-cracking here. And as always, we combine it with with other measurement techniques. So we would have laser measurements, LVDTs, things like that on the bridge to learn about the deformations under the applied loading. So if we look into proof loading of bridges, why should we proof load a bridge? Why should we just take a bridge and proof load it? We have different levels at which we assess bridges. The first one is we just make a hand calculation, and if it passes, then it's fine. We don't need to do any additional calculations. If we find that the hand calculation says that the capacity of the bridge is not enough, then that doesn't mean the bridge is going to collapse, but it means we need finer calculation techniques, techniques that take more time, but that give us more information as well. So it would be linear finite elements. If we still need more information, we go to nonlinear. If we need still more, we go to probabilistic analysis. And we can couple probabilistic with nonlinear finite elements by taking into account a random distribution of a material like concrete, which is it's a combination of stones and cement, so the properties change in a given area. So we can take that random field into account when we make nonlinear finite element models. If we're still doubting, or if we have a large set of bridges of the same type, we might test one of them and learn much more about it. We proof load. In the proof loading, we don't want the bridge to collapse, so we we defined previously what are the levels of load that the bridge needs to support when we can say this is okay, or we have to post a bridge, put a little sign saying maximum this much of tons. So we don't want any permanent damage in the bridge. And we have these different levels. One is called unfit for use. If we have loading below that, it's unfit. You have to replace the bridge. If you pass that load level, it's good, but we might require maintenance. Anything that's below the repair level requires maintenance. Everything that is loads above it is good to go. So why do we proof load? Well, we want to extend the service life of the existing bridges. Most bridges were built for 50 years of design life, and especially in countries in Western Europe where most of the road network has been rebuilt after the Second World War, most of these bridges are now at their retirement age. But the idea is, well, should we demolish all of them, 1 million euros per bridge, or can we extend their life? And the answer is yes, but of course we need to know more about them. Because of course the materials, such as concrete, they are not the same as the material was 50 years ago. It has undergone some deterioration. So we want to know the effect of that. And one thing that we did last summer is we tested one bridge until failure. Not just proof loading, but we actually tested until failure to get information that is valid for the entire bridge stock. And that bridge was called the Ruitenschildbrug. So we tested to have an idea of the real capacity of the bridge. And this was a special case because the bridge was scheduled for demolition, because on the other side of the bridge there is a lake and tall boats cannot pass. So it was already scheduled for demolition and given into the hands of researchers to learn something about it. What we did during the testing is we wanted to study the cracks and deformations for all the different levels of load that were applied, and to listen to the concrete, to listen to the cracks, we used acoustic emission. Not just one team, two teams. We had a team from Germany, from University of Leipzig that came to measure, and one of my colleagues was measuring as well, because we want to learn as much as we can about acoustic emission. And as I said before, unlike any other proof loading, this bridge could actually be destroyed. So it was maybe from the science perspective, a little more fun. And I have a short video about testing of this bridge. Not just the arrow. Sure. Thank you. Yes.
Vele van onze bruggen en viaducten zijn gebouwd in de 60 en de 70 jaren van de vorige eeuw. En bereiken zo langzamerhand het einde van de beoogde technische levensduur ten tijde van het ontwerp. Daarnaast is het zo dat vele van die constructies inmiddels zwaarder en frequenter worden belast dan waarvan uitgegaan was bij het ontwerp van die constructies. Dat maakt dat diverse van die constructies inmiddels niet voldoen aan de criteria die er aan stellen als we die uitrekenen met de gangbare rekenmodellen. Dat betekent echter niet dat die constructies niet sterk genoeg zijn, dus dat ze niet voldoen. En dus is het heel belangrijk om aan te tonen wat de werkelijke sterkte is van die constructies. En daar voeren we onderzoek naar uit.
Nou, wat wij doen is plaatsen een heleboel gewicht bovenop de brug om te testen of de brug sterk genoeg is om dat gewicht te houden. Hier achter mij zien jullie de opstelling daarvoor. Daar staan een aantal ballastblokken van kranen die op de brug aangebracht worden door middel van een gecontroleerd systeem. En met die ballastblokken gaan wij dus heel voorzichtig de brug steeds iets verder naar beneden drukken. Mag gelijk doorgaan naar een belasting van 50 ton.
Oké, zo ja, 50 ton.
Dank je.
Peter, we kunnen door naar stap nummer 17, 100 ton. Ja, 250 maar een ton. En ik hoorde iets klappen.
Blijft de belasting stabiel?
Even kijken zo, ja. Ja, nog steeds 250 ton.
Dank je.
Ik kan vertellen dat de proef succesvol verlopen is. We hebben vanaf 350 ton een buigscheur gevonden die plastisch ging vervormen. Dus bij de maximale belasting tot 380 ton bleek er een scheur ontstaan te zijn van 3 mm die over een lengte van 5 meter over de breedte van het brugdek zich uitstrekte. Verder blijkt bij deze proef ook dat de pijler 1,5 centimeter gezakt is. Zo hoog was de belasting. Dus we zitten wel op een extreem hoge belasting natuurlijk. Wat voor ons heel belangrijk is, is dat er geen dwarskrachtbreuk is opgetreden.
So you could see in the video as well all the measurement techniques that were on the bottom of the bridge to listen to the bridge and to also measure the deformations. So just to summarize a few things, even though you might not think of engineering as a field that has very much to do with sound, there's a lot of applications. We're using sound for measurements and we're thinking of sound when it comes into material mixes for pavements or design of buildings. And when we looked at bridges, we saw that we can have better inspection with non-destructive testing techniques, that acoustic emission is becoming very important for measurements, as well as for using it during proof loading of bridges. And that concludes my presentation for today. Thank you.